Hey guys, this is Carrie, and this is Lesson 4 from Unit 9, How Computers Work. So, we're going to be talking about the internet today, but before we do, let's review some of the things that we've learned. So in Lesson 1, we drew an important distinction between something called RAM memory and hard drive memory. So RAM memory, and on the other hand, hard drive memory. Now, hard drive memory is all of the files saved to your computer. So you might notice that it's like a seemingly infinite amount of files that you can save to your computer. You can save a huge number of files. A huge amount of memory is available, of hard drive memory is available. And we talked a lot when we were introducing this idea of the computer hardware that is analogous to structures and functionality within the human brain. So hard drive memory is analogous to like all of the facts that you know. So I don't know, the actors in your favorite movie, your favorite 7 songs, who your math teacher was in 4th grade. Like all of those things are somewhere inside of your brain's hard drive memory, but you probably weren't currently thinking about those things before I said them. Now that you started to currently think about those things, what happens in a computer is when you start to think about something, when you double click on a file to open it, a song or an image or a movie, it loads that file from its hard drive memory into its working memory, which is called the RAM memory. And this is sort of what we do with our brains, right? When we start thinking about something, it's no longer this abstract fact that we know, it's something that's currently being thought about. So similar to humans, if you tried to think about all of the things that you knew, your brain would like explode. Well, the same thing is true about a computer, right? If you tried to open all of the files on your computer wouldn't be able to handle thinking about all that stuff. So RAM memory is actually, instead of having a huge amount of space, it's actually very limited with what you can think about. And let's see, what else do we want to talk about with these? I don't know. So as you continue on with this unit, one of the major goals, right, is to think about our AP Explore task, which will be the final project for our AP exam. And what you're going to be doing is you're going to be researching a computational device. And you're going to be thinking about how does that computational device store data on it. So you can think about what information will be in the working memory, the RAM memory. What information will be in the hard drive of that device. And how does it communicate back and forth between the two different functions. So related to this is, if we looked at computer memory, instead of seeing a word or an image or a song, everything inside of your computer is actually stored as a 1 or a 0. So all computer memory is a 1 or a 0. And a single 1 or a 0 is the smallest amount of memory on your computer, and we call that a bit. So let's check out this problem. So using the ASCII table below, convert the word math to binary. This is how your computer stores this word in its memory. So if we went to the word math, M-A-T-H, we can look these up in our table. M is, M is lowercase, okay, uppercase m, so the code, okay, uppercase M is 77, lowercase a is 97, lowercase t is 116, and why did I write B? H is 104. So those are the decimal equivalents of these letters. And we're using decimal not to mean it as like the period. We're using decimal to mean it as a base 10 number. So these are the base 10 versions. So the last step here is to convert these to binary. And I think the easiest way to do this is to make a table. So we've learned that when we use ASCII, the computer uses not just 1 bit, but a set of 8 bits. And 8 bits are always referred to as 1 byte of data. And that should be very familiar terminology. If you think about an image on your computer, it might take up 24 megabytes. Or your whole phone's hard drive might be 32 gigabytes. And that's the byte from that unit. So let's set up our bytes. So we're going to have 8 slots for our byte because we have 8 bits. So 1, 2, 3, 4, 5, 6, 7. Okay. And I'm going to erase these arrows. All right, so let's see. This is going to be the 1 space. Nope, too light. Can't read it. The 1 space, the 2 space, the 4 space, the 8 space. And these are all just coming from doing times 2 because binary is base 2. The 16 space, the 30 seconds, the 64th, and the 128th space. All right, so to make 77, we need 0 128ths. We need 1 64. That leaves us with 77 minus 64, 13 left. So 13 left, we don't need any 32s, we don't need any 16s, we need 1 8, 1 4, and 1 1, because 8, 4, and 1 makes 13. We don't need any 2s. For 97, we don't need any 128ths. We need 164, 132. That gives us 96. So then we don't need anything else except a 1. For T, we need 116, so we don't need any 128ths. We need a 64, a 32, and a 16, I believe. So 64 plus 32 plus 16. That's going to be 112, so then we also need a 4 and nothing else. And for 104, we'll need 0 128ths, but we'll need a 64, a 32, that's 96. 96 plus 16, that's going to be 102, 112. That's too much, so we can't handle having a 16 here. So we'll need 96 plus 8. Yeah, that's 104. Okay, awesome. And so we've got our ASCII conversion here to a byte of data for each letter. So in your computer would probably store this as math first, so M first, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, and now here we get the division. It wouldn't necessarily, oh, sorry. This is the first byte, sorry. So this would be the M. The next byte, your computer wouldn't put a space there. Your computer would just know to read through these 8 at a time, so then we would go to A, and A would be, let's do A in blue, 0, 1, 1, 0, 0, 0, 0, 1. So that's your second byte, which would be your A. Next up in green, you'd have your T byte, and that would be 0, 1, 1, 1, 0, 1, 0, 0. And these are all going to be 8 bits long because it knows that each 8 bits is going to be a letter. And then finally, you have your H, which would be 0, 1, 1, 0, 1, 0, 0, 0. So pretty remarkable. This is what the word math would look like inside of your computer's hard drive. And there's your computer's very fast at doing the calculations that we just did. So these calculations, it's easier for your computer to specialize in specific types of calculations. Instead of having like different kinds of calculations for everything, it turns out that we reuse this idea of a byte when we talk about colors, which is about storing images in your computer. So in the last class, we learned that an image in your computer is stored as each pixel on your computer gets its own information. And the pixel for that image is going to be a combination of actually 3 lights. So if you were able to zoom in with a microscope on your computer screen on a single pixel, you'd actually see inside of your screen 3 diodes, a red diode, a green diode, and a blue diode. And these would be making up the entire pixel. So this is actually hardware. Your computer only has the ability to make red, green, and blue light. But because pixels are so tiny, when we combine these colors in the right proportions to each other, similar to combining red, yellow, and blue for primary colors, it actually makes all of the colors that we can see on our computer. So we're going to decode this number from our computer's memory into an RGB number. So the same way as before, each of these amounts, each color gets 1 byte of memory, which means 1 byte is, just like we said before, 1 byte is still 8 bits. So it's reusing that structure from ASCII because it's so valuable, that 8-bit chunk of memory. So here we go. 1, 2, 3, 4, 5, 6, 7, 8. let me do a different color here. So this one will be the green byte. So 1, 2, 3, 4, 5, 6, 7, 8. And then we've got our blue diode, which will be the last one in RGB. So the blue byte will be 1, 0, 1, 1, 0, 1, 1, 1. All right, so to convert each one of these, you can basically make the same table that we made before. So it's a byte, so these are going to be 128. Actually, it's probably easier to label these from left to right if you don't have that much familiarity. So this is your ones place times 2, 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 and then we've got 1, 2, 3, 4, 5, 6, 7, 8, one for each binary digit, one for each bit in a byte. So if we put the red number into these place values, that's going to be, whoa, got too much there. This one's going to be 1, 1, 0, 0, 0, 1, 1, 1. So we have a 64, a 64, sorry, we have a 128, a 64, a 4, a 2, and a 1. Combining those things together, let's just use Siri to do this. 128 plus 64 plus 4 plus 2 plus 1.
The answer is 199.
Cool. Next up, we'll do in green here. 0, 1, 1, 0, 1, 0, 1. Whoa, did I miss one? 0, 1, 1, 0, 1, 0, 1, 0. Okay, it's much easier for your computer to do this than us, but I think it's useful to see what's happening behind the scenes a little bit as we learn sort of the details about the computer. All right, so this time we're going to have a 64 plus a 32 plus an 8 plus a 2. 64 plus 32.
Sorry, I didn't catch.
64 plus 32 plus 8 plus 2.
The answer is 106.
Great. And then lastly here we'll have the blue amounts, which is 1, 0, 1, 1, 0, 1, 1, 1. So it will be a 128 plus a 32 plus a 16 plus a 4 plus a 2 plus a 1. 128 plus 32 plus 16 plus 4 plus 2 plus 1.
It's 183.
Cool. All right, so we've got our RGB values here all set up. So we can write our color as red, green, blue, and if we were putting it as a background for our web page, we'd write it like this: 199 for the red amount, 106 for the green amount, and 183 for the blue amount. So it looks like this color is going to be fairly bright because these values are close to the maximum value, which is 255. So this is going to be a bright color. It's also probably got more red and more blue than it does green. So I'm thinking it's going to be a bright magenta-y color. And we'll put a question mark there. And then if you go to your computer, and I won't be able to do this on the iPad, but if you go and you Google RGB 199, 106, 183, you can actually see what color this would be. It's actually, you're pretty accurate. It's not quite as bright as I would have thought. It's more like a muted magenta color, but very cool. All right, so if you want to see that color, please Google that. All right, so one of the important functionalities of computers is how they work independent of each other. But another important functionality is how do computers connect to each other? And in order to think about that, nowadays, the internet is a fundamental part of how computers work. So the rest of this week, we're going to be talking about the internet. So here's an introduction to the internet. We actually kind of already drew this diagram before, right? We thought about our computers, whether it's a laptop or a phone, any device that's connected to the internet. When you when you open a program on your computer that can browse the internet, that program is called your web browser. And an example of that we've been using all year is Google Chrome. So that's a program that's used to surf the internet, or to, I guess they used to say surf the web, but they don't really say that anymore, to go on the internet. Safari is another example, or Firefox, or Internet Explorer. So when you go on to that program, you have a web address bar, which is where you type in the website that you want to go to, and this is called a URL, the website that you want to go to. So you type in the URL there, and then all of a sudden your computer connects somehow, magically, to something that's called the server computer. So maybe this is Google's server computer. Actually, I don't want to use Google because we already said Google. Let's say it's Wikipedia. Wikipedia's server computer. That's not how you spell server. And then when your computer connects here, it sends something called a GET request. And that's basically, hey, get me the webpage for Wikipedia. And it sends that message like a little chunk of information through a variety of different things that we'll talk more about today. And as that message progresses through the internet, it reaches the server, and then the computer sends back the web page. And the web page is formatted as a .html document, which might include resources like .css for cascading style sheets or .js for functionality. So it sends the web page back. As a .html document. And you guys have been building .html documents all year pretty much. And when you open a .html document in your web browser, it renders all the images, renders all the style, and takes care of displaying it for you. So it's like a recipe of how to build the web page, where like, okay, here's the header, and then your browser knows, okay, put that header here, and here's an image, put that image here, and here's a paragraph, put that paragraph here. And all of a sudden the web page is constructed on your computer. All right, so today's lesson and the future lessons that we're going to be talking about in this unit are mostly about what's happening in this middle section. There is a set of interesting protocols that we're going to be studying, interesting set of rules for how your computer connects to server computers and gets the information that it wants. So the first part about this is called HTTP. And this is hypertext transfer protocol. And so this is the first of the rules that the internet uses in order to send and receive information. And this is actually the overarching name for something like the GET request. So this is a protocol, and you're going to hear the word protocol a lot in this unit. Set of rules for how your computer sends requests for data and receives the data. And the reason why we have all of these protocols with the internet, I think, is best highlighted by something we've learned. I don't feel like I'm spelling that word right now. Let me just Google it. Yeah, okay, I'm spelling it right with the O. All right, so protocols are really important, and I think it's highlighted by our situation with remote learning. So what we found is that something like Sublime Text doesn't necessarily work in Chromebooks. So we've had to debug some issues around that. Or .zip files have different ways of unzipping those .zip files so we can access the data inside, depending on whether you're using a Mac or a PC. Now, the internet sort of is amazing because it works on all systems equally good. And in order to guarantee that it works on Windows computers, Macs, iPhones, Androids, whatever device is connected to the internet, there are a set of rules that are created for communicating called these protocols. And all devices on the internet follow the same protocols, and that way all devices on the internet get the same access to it. So HTTP is Hypertext Transfer Protocol, and it's a set of rules for how your computer sends requests for data and receives the data. So an example of this is the GET request that we had above. So it's actually very simple. Your computer will send out a message, and the message will say, hey, get me Wikipedia, get me wikipedia.org. And that is and That's pretty much all that's included with the GET request, except it also includes who that message is coming from. So I don't know, in my case it would be Carrie or something. We're going to talk a little bit more about how this looks and how this looks later on in the lesson, but basically this is an example of something called a GET request. When Wikipedia gets this request, it's going to be like, oh, hey, I got to send Carrie wikipedia.org, and it will send it back to me. And that's like a special computer that's just responsible for sending this HTML document to anyone that requests it. And it doesn't really look like a computer. If you Google a server computer, it will look like a monitorless, it doesn't have a screen computer. Okay, so let's talk a little bit about the design of the internet. So when the internet was designed, there was a big question, which was, what should this structure inside of the internet, the intermediary between computers and servers, actually look like? And so there were two ideas for this. One idea was that the internet could be a centralized network. And so what you'd picture here is maybe here would be all of the servers. And then if you want to get information from any of those servers, all of us, Carrie, could connect. You could connect directly to all of the servers. I don't know, your parents could connect directly to all of the servers. Your friends, one would connect. All of us would be connecting to the same servers. And this is something called a centralized network, where all of the connections go to the same place. An alternative for this is you might have the servers separated. So maybe you'd have Wikipedia here. You'd have Google here. You'd have, I don't know, Facebook here. And then in between all of these, you'd have a connection to various other things called routers. And you'd make a little bit of a web of connections where you could connect directly to these things. So now let's see, maybe Carrie is here. And maybe you connect here. And this is called decentralized. So when the internet was being designed, there was a choice between these two design philosophies. So a centralized network has some advantages, right? You've got one place to maintain all the information. And that's kind of like how maybe organizationally that seems a little simpler. Just one place that has all of the web servers and you just connect directly to it. However, this is a major weakness. So as we were inventing the internet, we were very concerned about the Cold War. And if this place got bombed, all of the internet would go down for the entire United States or the entire world. And that's the danger of having a centralized network, is that it's easy to target that one location. Because all the computers connect directly to it, it has a big problem with that. A distributed network, on the other hand, even if you were to, I don't know, shut down Google, let's say you bomb where the Google web server is, or you hack into that, the rest of the internet, because it's not in the same location, is actually still accessible. Related to this as well is this idea where if you were to sever a connection, let's say this cable goes down because, I don't know, this fiber optic cable gets destroyed accidentally by a submarine or something, because a lot of fiber optic cables go underneath the ocean to connect things. Well, I can still connect to all of the websites because I can avoid that connection by going this route instead. And then even if this one gets destroyed, I can still get all the information on the internet. So a distributed network has a couple of properties. We would say that a distributed network is fault tolerant, because even if something goes wrong, one of the wires shuts down, there are alternative solutions available. All right, so the following diagram shows a computer network composed of computers A through F. If there is a line between two computers, that means there is a direct connection between the two computers. Note that this network is designed so that there are alternative paths between computers. An X on a line means the connection is currently broken. So this is a little model for the internet here, and this is one of the AP exam questions. Of course, you guys are not going to be taking the multiple choice AP exam this year, but I think it's still useful for getting a feel for the structure of the internet. So if we want to send a message from computer A to computer D, given the current status of the network, which of the following computers would the message be required to go to in order to reach the destination? So it looks like to go from A to D, we could go A, B, E, D. We could go A, F, E, D. It doesn't have to take a fast route though. It could go A, C, B, F, E, D. And then we'd be able to get to computer D. But it looks like no matter which of these routes we go through, we need to go through, okay, we don't need to go through computer B because this blue route avoids computer B. We do need to go through computer E. All of the routes go through computer E because that's the only connection to D. And computer F we can avoid by going with this gray route, A, C, B, E, D. So it looks like only computer E. So even though two of the routes were shut down here, two of the wire connections between computers, this web of connections, this net of connections allows us to still communicate between computers. All right. Let's do one more of these. The figure below represents a network of physically linked computers labeled A through F. Computers with a line between them can communicate directly to each other. And if two computers do not have a line connecting them, they must go through at least one other computer to communicate with each other. Which of the following statements about security in the network is true? Computers A and D need to communicate with at least two additional computers in the network in order to communicate with each other. All right, so if we started at A and we want to go to D, I think they have a direct connection right here. So I think that because of the direct connection, we don't need to worry about going through other computers. So this is false. Computers B and F can communicate with each other without additional computers being aware of the communication. So if we want to get from B to F, there is no direct connection there. So we'd have to go through E maybe to get from here to here. So this one is also false. Computer E could be like a web router, it could be a different kind of server, it could be a variety of things, but we have to go through computer E to get from B to F. So both of these are false, so it's neither 1 nor 2. So a key feature of the internet that we discussed is the internet is redundant and fault tolerant. Redundant means that there is more than one path from one thing to another. Redundant is like when you repeat yourself and you say the same thing over and over again, which is not usually a valuable thing, but it's actually a valuable thing when it comes to the internet because if you have multiple paths to the same destination from the same starting point, then even if one of those paths breaks down, you can find your way from one computer to the other. And this connects really well to this idea of fault tolerant, which is even if something goes wrong, the system doesn't break. And we rely on this with the internet, right? Cables go down all the time. Networks have temporary outages. Servers go down. And this doesn't shut down the whole internet. It might make things inconvenient for a while for you, but it doesn't actually mess up the whole internet. So if you could take a minute now and try to write your answer to this question to see if you understand it. How does the decentralized structure of the internet illustrate these properties of redundancy and fault tolerance? And when you're done with that, please do question 5 as well. All right, so continuing on. Which of the following best describes the basic idea of fault tolerance? Try to answer this question on your own. What is the primary reason that routing on the internet is redundant? Okay, we can try to answer this one together. Many routers were established before standards for routing existed. So the little computers in the network that send you on these variety of different routes, all of these nodes on the web, the points on the web, these are called routers. And they tell you which route to send your message in. So you might go from one router to another router to another router to another router to another router. And these are called routers. All of the little nodes, all of these little computers. And so actually, it's not a technological issue. It's actually a design philosophy. It's intentional. There is no monitoring to make sure that repeated paths don't exist. Well, we want repeated paths. So that's out as well. So the primary reason why the internet is redundant is that networks are still available in case a path or router fails. So even if this router breaks down right here, or this path breaks down right here, there's an alternative path by which this computer can access this computer, or this computer, sorry, this computer. So we could go this way instead. And that's really important because cell towers go down, or computers go down, or routers go down, or routers are being updated, and you can still use the internet as all of this is happening. So it's built into the system intentionally, this redundancy. All right, so try to do number 8 on your own. So I think what we're going to do is we're going to cut the lesson here, and we'll save the rest of the lesson for Wednesday's class. And I hope you guys have a bit of a better idea for how the internet works, and we're going to continue to expand on that. So the most important takeaways from today's lesson are when your computer wants to get a website, it sends a hypertext transfer protocol message. And those look pretty simple, like, hey, get me the web page. And then they send the web page back to you as a .html document like the ones you've been making this year. We're going to look a little bit more about the details of how we send things on the internet in the next lesson. But then we looked today at how the physical internet is actually structured. And the physical internet is a web of different connections, a network of different connections, hence the net in network. Net in internet, sorry. Internet. It's a net of different connections. And that allows the internet to be redundant. It has multiple paths from one path to another, which is good. Because even if something breaks down, things still work out. And that's the idea of fault tolerance. So we'll talk a little bit more about the internet